Okay, let's get started. So this is the last lecture, and I'll try to be quick, but this is such an exciting topic. I have so many slides. So it's probably not going to be quick, because we'll do other things too. Like you'll give me the cookies you all. So this is statistics for Lab 5. I'm really happy with the Lab 5 and Lab 6 results, actually, as you will see. The median is 100, as you can see. Mean is 93, so you can guess what kind of distribution this is. The distribution looks like this, which is good. Like more than half of class got 100, or whatever that bin is over there. I believe that bin is more than 90, which is good. And no one got below 50, which is nice too. And more importantly, well, maybe not more importantly, but importantly, lots of people did extra credit, so I'm really happy about this. So I'll recognize people here. Dosi, is she here? No. Jonathan? No. I guess extra credit winners are. That's number 5. So you were graded based on a scale, based on how well you documented what you did, how well you performed. So this is number 5. So this is not the top yet, but it's still important to do extra credit. Tang Fei? No? Eric and Albert? Come on, Albert is always here. Yeah, there you go. I couldn't see you. And number 2 is actually a lot. This is almost perfect score. Changsheng. Yeah, there you go. Fazle. Jackie. Jeremy. And Nicholas. Oh, there you go. Good, people are coming in. And number 1, you're all wondering who number 1 is, right? There are lots of number 1s, actually. So lots of people did the extra credit. Aaron, Bailey, Max. Where's Max? Mangjae, Jiang, and John. John is there. Mangjae and Jiang. Okay, we didn't repeat multiple people, right? So I'm happy because 16 people actually did the extra credit. This doesn't mean that you have to, but I think this is good. So it's really a record for 447 so far. So that's why you get this extra lecture. That's not why, actually, but you would have gotten it regardless, because this was prepared after the fact, after I knew that I was going to give this lecture. So congratulations. You can congratulate your fellow students also. And let's go to Lab 6. So that's also graded. You should see your grades. And this is actually very similar. Unless actually, this looks like there seems to be a mistake here, right? Did I get these right, or? It looks like the same. I guess it's my fault. Anyway, ignore this. The grade distribution is correct. So most people actually got the highest possible score. I guess some person didn't submit, or you'll figure out what's going on. And there were fewer extra credits. Actually, this is from top to bottom. Albert got the best performance with his prefetcher. Fazle got the second best. And Bailey got the third best, I think. And you can figure out what kind of test cases were used. So it's good that everybody's doing extra credit. Are we missing anyone else, by the way? I guess this was too close to the midterm that not everyone submitted. Yeah, I know some of you regularly submit extra credit, but this was at a bad time. Well, these are the people who win cookies, actually. And actually, I have lots of cookies. And they will regret that they didn't come today, because you get a choice if you're at the top. I was really happy to find these Turkish cookies at Giant Eagle. They're not traditional Turkish cookies, but those are tasty. You had these before? They look tasty, yeah. So these are the Turkish cookies. They're not the best Turkish cookies, but at least they are the ones that exist at Giant Eagle. And we have lots of heterogeneity. Some of them are healthier than others, I think. But you guys are young, so you don't care, probably. There's a whole grain. And this will kill you, probably, in the long run. Those are good. Let's see. I think these are new. For instance, I guess that's enough, right? But let's go through this first. These are the people who did extra credit for all labs -2. Is this correct? 5? Yeah, we have 5 labs where we have extra credit. Obviously, we don't have lab 7, and lab 1 didn't have extra credit. And if this is incorrect, let me know. But John, Jeremy in the back, Teng Fei, who was not here, I think, still not here. So maybe you can text him or email him so that he doesn't lose his cookies. Jiang, yes, and Changsheng. So you'll get cookies. Maybe we'll distribute them in the middle so you can. Although I don't know how the lecture will go by you looking at the cookies over here. That's oh, okay. All -1. Albert, did you do 5? Okay, you didn't. You missed 1 lab, right? And I guess all is Bailey. Congratulations. So maybe you can pick your cookie. No, go ahead. You earned it. You'll get the Turkish one? I can give it to you if you like one of these.
Which one's the best?
I have no idea. I like this one, but that one is good too, I think. Albert, which one do you want?
I'll try the Turkish one.
Which one? The apple one or whatever?
Or whatever the other one is.
Yeah, this looks better. Yeah, try the apple. Apple can be dangerous. And John?
I'll try one.
No, you get one. You get one full.
Oh, man.
All people here get one full.
Apple is dangerous. Otherwise, I would go with the interesting one.
You're full grain? No.
Actually, yeah.
Yeah?
Yeah, the big new ones.
Are you sure?
Yeah.
You don't have to go healthy.
That's okay.
Actually, I don't know how healthy these are, even if they're full grain. Jeremy? Turkish one, so you can pass along. Don't eat it while passing along. Teng Fei? Teng Fei is not here, right? You'll take his? Later, if he doesn't come. Xiang? Which one? Something later, but you have to pick, otherwise people will get it. Why didn't you guys come here? Because you're the last 2 left. And pick whatever you would like to get. And you can text Teng Fei in the meantime if you know him. Otherwise, his cookies will not go to waste, but will go to everyone else over here. Okay. Okay, we can move on. And these will be distributed in the middle. So try to get hungry and finish your pizzas until that time. Okay, so you know the final exam is coming up. I'm not going to go through this again because we have things to cover. And you know this one too. I'm not going to go through this again. Well, okay. I guess let's jump into the material, right? This is going to be a lecture about main memory system, which we talked about a lot so far. And I think I've shown you this picture before. But this is a critical component of all computing systems. Regardless of what computing system you build, you'll need to have some working storage. Main memory is really working storage. You put the data that you work on in main memory, and this is more persistent storage. But we'll see later toward the end of this lecture that these are kind of merging going forward because of the emerging memory technologies that we're seeing today, non-volatile memories. But this system must scale in many, many dimensions to improve performance and efficiency. It should scale in size, technology, efficiency, cost, and the management algorithms, of which we've studied a lot, like memory controller, scheduling mechanisms. It should scale to many, many nodes, and it should scale in capacity and efficiency and everything over here to maintain the performance growth and technology scaling benefits we've seen. And this is a shared resource view of the main memory system. I believe I've shown this picture a while ago, maybe in the first lecture, kind of. If you look at this, most of the system today is composed of things that are related to storing data or moving data around. And cores are a very little fraction of what you have. And it's a shared resource, basically. Memory is a shared resource. It's the biggest shared resource that you have in systems today. So I'll talk about the state of the main memory system to motivate some of the emerging memory technologies that people are looking into today. And these are actually becoming real in many systems today. there's some recent technology, architecture, and application trends that lead to some new requirements and exacerbate old requirements from the memory system. And DRAM and memory controllers, as we know them today, as you've seen them in the basic DRAM lecture and basic memory controller lecture, are unlikely to satisfy all of these requirements going forward. If they're not, they will be unlikely. And there are some emerging technologies that are pretty interesting that happen to be non-volatile at the same time, just like hard disks, or just like flash memory, SSDs, that enable new opportunities. And we'll see one of those opportunities toward the end of this lecture. And that can also potentially satisfy some of these requirements. So this lecture will be about the second one, but I'll motivate it with with some other things such that you can see how this fits into the picture. So it's an exciting time to be an architect because this is a time where you can do a lot of changes in the memory system, especially today. Because memory is the biggest bottleneck in many, many applications, especially if you're running data-intensive workloads. And once memory, like non-volatile technologies become faster and faster, storage becomes less of a bottleneck in many of these systems. So we need to rethink the main memory system to fix some of the issues we're having with DRAM. And you've seen some examples throughout this course how we are rethinking some of the DRAM issues and enable some of these emerging technologies while satisfying all of these requirements. So let me go into some of these trends that are affecting main memory. I think I'll go through these relatively fast, talk about some major solution directions to fix some of these issues, and then derive some requirements from an ideal main memory system. Now, you already know these requirements, but I'll reiterate and jump into the meat of the lecture, which talks about how some of these emerging technologies can be used, what are they, and how can they potentially enable something closer to an ideal main memory system. Okay, so you already know these three, I think. So we need more memory capacity and bandwidth, and actually quality of service over here too, but you already know that well. Energy and power is a key system design concern today, and DRAM technology scaling is ending, and we'll take a look at all of these. So why do we need more capacity and bandwidth? Because we're adding more cores, which has more concurrency, and you also have larger working sets, and you need more demand for memory. And these are old, this is an old slide, as you can tell, and these are old machines. New machines have even more cores, right? So if you look at a GPU today, it has lots of cores, as NVIDIA calls them. They're not real cores, but if you put the streaming multiprocessors together, it's a lot of bandwidth demand. So emerging applications are also data intensive, and increasingly they will be more data intensive. And on top of this, we will consolidate many more applications on virtual machines such that they share main memory. And this is a trend you see in many, many systems today. Basically, in cloud computing and servers, you'd like to consolidate more and more applications on top of the same multi-core chip such that you get better efficiency. In GPUs, you have many threads, and they will be running multiple parallel applications. That's the trend, even though they may not be today. Believe me, they will be very soon. And in mobile systems, you already have, in my cell phone somewhere here, many applications running, right? And some of them are interactive, some of them not interactive. So you have lots of demand for main memory, both capacity and bandwidth. And this is an example that shows what's happening, at least so far, in terms of the trend, in terms of what's happening to the core counts and what's happening to the DRAM DIMM capacity. Well, this is core counts, actually. Core counts are increasing. They're doubling every 2 years, approximately. And DIMM capacity is doubling approximately every 3 years. Which means that if you do the calculation, memory capacity per core is expected to drop by 30% every 2 years. That's a terrible thing, right? If you're running writing a single-threaded application, you're getting less and less capacity on average. Not good. Because people are actually there should have been another slide over here. There's this vicious cycle, if you will. Computer architects improve processor performance or system performance, and software developers basically write more and more inefficient software to take advantage of that performance, to add more features. And that's the vicious cycle of software. Software industry has actually banked on this to become I guess almost $1 trillion industry these days. So once that cycle breaks, which is one of the breakers of that cycle, basically if you don't get more memory capacity, well, too bad, you cannot add more features. Or if you add more features, what happens is your computer slows down. And I'm sure you've noticed this. Whenever I upgrade my iMac, and I've become tired of upgrading it recently. I wish Steve Jobs was still alive such that we didn't need to deal with this stuff. But but whenever I upgrade my iMac, if I don't add extra memory, it seems like it's slowing down. It happens. You've noticed it, right? Am I the only one? Okay. Okay, so this is bad, basically. And actually, if you draw the trend for bandwidth per core, it's dropping even more significantly. And I'll leave that for you to do. So these are the main reasons why we need more main memory capacity, bandwidth, and quality of service. We'll talk about quality of service. We'll talk about quality of service quite a bit, so we're not memory interference quite a bit. The second trend is main memory energy and power is a key system design concern. In every system, actually, today. This is data from IBM servers in 2003. They've studied these big iron servers at IBM, and they found that approximately 50% of the energy of these servers is spent in off-chip memory hierarchy. That's a lot, right? 50% of the entire system of the data center. Think of it that way. And DRAM consumes power when idle and needs periodic refresh. And this is a problem with DRAM scaling, as we've talked about in the first lecture, later on in the DRAM lectures too. So we're not going to cover this that much, but we'll see how emerging technologies can potentially help over here. And the third trend, which we briefly talked about, is DRAM technology scaling is ending, because it's becoming more and more difficult to reduce the size of the DRAM cell. And people have projected that DRAM will not easily scale below X nanometers. And X has been changing a lot, but it's becoming harder and harder to reduce X without increasing the cost significantly. Because what happens when you reduce the size of the DRAM cell, well, this is the DRAM cell. When you reduce the size of this, it becomes, both of these things become less reliable, and the cells start interacting with each other in less and less predictable ways, because you have inter-cell coupling, capacitance coupling effects. Whenever you program one cell, you may be affecting the capacitance on another cell. This is actually a very well-known effect in many type of memories. Flash memory has this problem. DRAM is having this problem also in even real chips today. So it's becoming more and more difficult to operate this reliably as you reduce the feature size of the cell. And this was the number that was assigned to X by the International Technology Roadmap of Semiconductors in 2009. They said scaling the cell beyond the feature size of 40 to 35 nanometers is very challenging. It is true, it has been true that it's been challenging, but DRAM manufacturers now can operate this at 20 nanometers or so. But their costs have increased. Their costs have increased a lot, and they're also having difficulties because, like one of my students, Jungo, is working on the problem called row hammer problem. In existing DRAM chips, he has demonstrated that if you keep activating a row repeatedly, the row next to it can get corrupted. You can have incorrect values over there without even touching that row at all. You never access that row. You never write to any row. You just keep reading a row repeatedly. The row next to it gets corrupted. And this happens in existing DRAM chips. You could buy some of them off the shelf today. So it shows you that how difficult scaling this is, because these errors have escaped into the field right now. Yes?
Is it even possible to only read from a particular row? Because when you read, then you're discharging those capacitors, so you need to recharge them.
That's right. So you need to activate and pre-charge. Activate, pre-charge, activate, pre-charge.
Effectively a write to the row from the sensor.
I guess that's true. You could think of it as a write. It's really a feedback loop, right? You're not writing a new value, but what you're doing is it's really a feedback loop between the sense amplifier and the cell. You could think of it as a write. You're right. You're right. That's a very good point. Because a normal write is kind of like that. You write into the row buffer, you drive the cells in the row buffer, and that drives the cell. But the reliability of the write is actually lower than the read. That's why I mentioned not even write, because you need to drive the row buffer, and that needs to drive the cells after that. That's a good point, though. DRAM is kind of interesting in that sense. You're really not, write and read are not that different from the cell's perspective. It's very different from the row buffer's perspective. Okay, so but it's clear that DRAM capacity, cost, and energy and power are hard to scale. And this is going to be even harder to scale going forward by reducing, as we reduce the size of this. And this is becoming more leakier also, as we've seen with the refresh problem, right? But if you want to operate this well, capacitor must be large enough for reliable sensing. And if you imagine you reduce this, the charge on this capacitor will reduce. How many electrons can you go to in this capacitor, right? And you'll need to sense them somehow. So that's the fundamental challenge with charge-based memory, as we will see. An access transistor is a little bit better, but not too much, because if the access transistor gets smaller and smaller, it becomes higher leakage and has less retention. The ERC path becomes harder to maintain over here. Well, harder to maintain such that the capacitor doesn't leak. Okay, So these are some of the trends, some of the problems with DRAM as main memory. DRAM capacity is hard to scale. Bandwidth is not terrible, but still not easy. And DRAM consumes high power due to leakage and refresh. And we want even more efficient memories going forward. And DRAM technology scaling is ending. This leads to a lot of other issues, like capacity, cost, and energy and power are hard to scale. Reliability is hard to scale. We may not even have reliable memory. So let's take a look at some solution directions. How can you fix this problem? There are two real potential solutions, I believe. One is you can tolerate DRAM by somehow taking a fresh look at it. And we've seen this, so I'm going to cover this very briefly and then move on to the next one. The second is find something else other than DRAM, right? And now you can start searching for that other thing. And there are some other things that are interesting, some emerging memory technologies. And if you can find them, if they look nice, maybe you can eliminate or minimize DRAM from the system. Right? You could say flash memory, for example. Well, it could be nice, right, if you could eliminate DRAM from the system by having flash memory replace DRAM. Except it's not good because flash memory is orders of magnitude slower than DRAM, right, and lower bandwidth. And there's other issues like a wear-out issue. If you keep writing to a flash cell, you degrade its reliability, and you can do only some number of writes to that flash cell. In fact, with multi-level cell technologies that you have in flash today, you could do only 1,000 writes to a flash cell. It's terrible, right? After 1,000 writes, the cell dies. If you use this as your main memory, it's terrible because you can do 1,000 writes probably in, I don't know, how many nanoseconds? You could do that calculation probably. Not even a millisecond, much less than a millisecond. Much less than a microsecond, you could finish 1,000 writes. So we'd like to find some other emerging technologies to do this. But the solution is really we should really be looking at both. And that's what people are doing in computer architecture today, especially my group and other groups in the area. And this leads us to hybrid memory systems, which I will also talk about. So let's take a look at the first solution. DRAM has really nice properties. That's why it's survived so far, right, as the main memory. It's been the main memory technology for a really long time, for decades. It was invented in 1965, I think, by Denard at IBM. But it's not scaling well. So how do we actually scale it? Well, maybe we should take a different look at DRAM. Maybe we should overcome DRAM shortcomings in a different way than just fixing the issues at the circuit level and the device level. And what does this mean? Well, maybe you should punt some of these issues to the system level. Maybe we should design the system and DRAM together. Maybe we should expose some of these issues to the memory controller, as we've seen with retention-aware intelligent DRAM refresh, right? In that case, the weak rows were exposed to the memory controller such that the memory controller can refresh them more frequently. You don't have a single refresh rate for DRAM. So that's kind of an example of this design. Maybe we should be looking at new DRAM architectures. Row clone was an example of this. TLDRAM, tiered latency DRAM, was an example of this, right? These try to overcome some of the issues with DRAM by adding heterogeneity and putting more functions into the DRAM such that you can actually overcome some of the shortcomings, like the bandwidth bottleneck. Row clone put some functions into DRAM such that you could do copying and initialization in DRAM, such that you don't use this bandwidth bottleneck. You don't get bottlenecked by bandwidth and energy at the interconnect level, which is one of the other scalability problems with DRAM, actually. And we could perhaps do better waste management, more efficient utilization of the system, right? And you've seen this with data compression, for example. So there are several key issues to tackle. How do we reduce energy? How do we enable reliability at low cost? How do we improve bandwidth and latency? And how do we reduce waste? You can think of this basically everything, right? You need to do pretty much everything to scale DRAM into the future, but maybe there is a way to do that by taking a fresh look at the design. Traditionally, DRAM manufacturers have been extremely concerned by cost per bit. Everything was cost per bit. Reduce cost per bit at the expense of everything else. And we've seen that with the latency trend, right? DRAM latency remained constant for a long time, but capacity has increased exponentially when we talked about tiered latency DRAM. Do you remember all of that, right? So maybe cost per bit is not the best metric. Maybe you give up some cost, but do something else, something more intelligent in DRAM such that this technology scales, such that you can relax some of the refresh problems. And maybe you design some DRAMs that are not tested and some are really heavily tested, and you have some heterogeneous types of DRAMs in the system. And maybe the application allocates data that's not that important to this DRAM that's not very well tested. And some data may be okay to allocate there. For example, some image data that you can reconstruct, or maybe some image data, if a pixel changes a little bit, you don't care that much, right? Whereas some other data, like pointers in a database, where you do transactions on, maybe better to allocate on a more reliable DRAM. But this way now you can specialize different kinds of DRAM, and you can actually still use DRAM in the system and scale the system. So there are a lot of other issues, and these are some of the papers that my students have written in the past few years related to this, some of which we've covered actually. Tiered latency DRAM is here, for example. Radar we've covered also, and I'm not going to cover all of these, of course. But, we've covered these, like retention-aware DRAM refresh. We've talked about reducing refresh impact. We've talked about reducing DRAM latency, tiered latency DRAM. We talked about accelerating page copy and initialization with row clone. And we talked about efficient memory compression very briefly, or compression in general in caches, right? Maybe I haven't talked about some of the other things, but that's okay. You get the key idea. Rethinking DRAM is probably a very good idea today. And in fact, DRAM manufacturers are very interested in that today because it's very hard for them to scale things. Okay, but let's take a look at the other direction, which is equally exciting. There are some emerging resistive memory technologies that seem more scalable than DRAM. And they happen to be non-volatile, so they can open up some new opportunities. So one example is phase change memory. This is actually expected to scale to 9 nanometers. This was, which will be achievable in 2022, according to the International Technology Roadmap of Semiconductors. And it's expected to be denser than DRAM because it can store multiple bits per cell. And we'll briefly talk about that when I talk about the technology. The problem is, these emerging technologies have shortcomings as well, so they're not perfect. There is no one universal memory. People have tried to find a universal memory, meaning a memory that's good at all metrics, that's the best at all metrics for a long time, and unfortunately no one has found it yet. And whenever someone claims that they found it, you've got to be very wary of it. You really need to have a big technological breakthrough to do that, and it's been very difficult for decades. I'm not saying it's not possible, depending on the technology, but it's difficult. The key question is, can we somehow enable these technologies to replace, augment, or even surpass DRAM if it's possible? And these are some of the works that we've been doing in this area, but I'll talk about some of these. So where does this put us? If there is no universal memory, maybe the future systems will look like this. And this is just one example. And we'll go into phase change memory in more detail, but maybe what we'll have is something like this. You have some technology over here that has some green characteristics and some red characteristics, and some other technology over here that has some other green characteristics and some other red characteristics. And you put them together off different controllers, maybe the same channel even. Maybe this is the same DIMM, I don't know. But it's the same idea. Basically, you have heterogeneity. And you design the hardware and software to manage data allocation and movement between these technologies to achieve the best of multiple technologies, to exercise the greens as much as possible while avoiding the reds as much as possible. Right? And this is actually representative for DRAM. It's comparatively fast and durable. But it's leaky, it's volatile, and it has high cost if it doesn't scale into the future, right? So phase change memory can be large because it has low cost, hopefully, going into the future. It can scale to very small feature sizes. And it's non-volatile, but it's slow. I'll show you some numbers. It wears out, unfortunately. It's like flash. It's not as bad. And it has high active energy, and we'll see the reasons for that. So if you have these different kind of technologies, maybe you can put them together and manage them and have a much better system going into the future. This is the idea of heterogeneity, as we've seen earlier. And increasing the systems will look like this. Actually, today, for example, there are people who are working on some die-stacked DRAM. It's not a completely different technology, but DRAM over here that's die-stacked, that has a logic, that has a controller, stacked together with other chips, and regular DRAM, commodity DRAM. So going forward, the systems you buy will look like this. And maybe that die-stacked DRAM, or maybe you'll have another channel over here that has phase change memory into the future. So it's not that far. It's not going to be very far. It could be closer than you think, actually. Okay, so we've covered a lot of this in this course. Let's try to focus on this one. But I think I'll have to emphasize one thing. There's one orthogonal issue that's regardless of technology. That's why this is really important also. And that's the issue of memory interference, which we've covered a lot in this course, right? Whenever you have multiple cores or agents, whenever they share this physical resource, main memory, they interfere with each other. And this interference is currently uncontrolled. This leads to uncontrolled, unpredictable, and vulnerable systems today. As we've seen in this course, I'm going to go through this really, really quickly. The solution is really building quality of service aware systems. And we've seen many solutions today, right? Hardware is designed to provide a configurable fairness substrate, memory scheduling mechanisms we've talked about, memory partitioning mechanisms, channel partitioning, we briefly talked about. Source throttling mechanisms, we briefly talked about, right? And software can take advantage of this substrate to configure the resources to satisfy different quality of service scores for different applications, right? And this is the future. This is already happening. People are already putting in these quality of service mechanisms into the memory hierarchy and designing software to take advantage of that. So I'm going to skip this because we've actually seen a lot of this, but feel free to take a look at it. Okay, well, let me derive some of these requirements from an ideal memory system and see if these emerging technologies, in particular phase change memory, can potentially satisfy this. This is another way of looking at it. Remember, when we first started the memory lectures after the first exam, I said ideal memory has some of these requirements. So now I'm expanding some of these. So traditionally, we want infinite capacity, zero cost, and high system performance, infinite bandwidth, and zero latency, right? These are already there. We always wanted these. We still want these. These have changed a little bit, as we will see. And there are some new requirements. Traditionally, we've been used to scalable DRAM. DRAM has been scaling, which is nice. But now it's changing. So we need something that's more scalable, that provides us lower cost, higher capacity, and lower energy. Traditionally, energy has not been a big deal in memory, but it's becoming even more because we have such big memories and they waste power in the entire system, as you've seen in the data that I provided from IBM, right? And this is a relatively new requirement. And quality of service support and configurability for consolidation, for example, is a big requirement that we have today. And you out of all people in the world will know this better, probably. This is not going to change also. So how does this change going into the future? Well, traditional requirements change a little bit because enough capacity is harder to maintain. So we want even higher capacity. DRAM is not scaling well, but we still want even higher capacity with data-intensive applications. And we want continuous low cost. That's the problem with scaling, right? Low cost is good, but you want it to continue also. And high system performance, higher bandwidth is important. Well, quality of service is here. Low latency is also important, but higher bandwidth is even more important going into the future. That doesn't mean that low latency is not important. Don't take it that way. I should probably make that red also in the next time. Okay, so some emerging resistive memory technologies can help, I believe, these parts, because they can enable higher capacity at low cost, and they're more technology scalable, and in some ways they're very energy efficient. Because if you are non-volatile, I'll call them NVM, non-volatile memory, because they happen to be non-volatile, because of the way they operate, they're very energy efficient when they're idle, right? Basically, you don't need to refresh them. A big scaling issue goes away. So let's take a look at the opportunity of these technologies. What is the promise of them? Basically, because DRAM is not scaling very well, we'll likely need to replace, more likely augment, DRAM with a technology that's more technology scalable. Feature size can be reduced without significant cost increase. And at least similarly efficient, high performance, and fault tolerant as DRAM, or can be architected to be so. And some emerging resistive memory technologies appear promising. And I'll tell you what I mean by resistive. This is very different from DRAM. DRAM is charge-based. These are actually resistance-based. So phase change memory is one example. Spin transfer torque magnetic memory is another. Memristors you may have heard of, or RRAM, RERAM, everybody calls it a different thing in another example. And there may be other ones. Actually, there are other ones, but they're too early in the development that they don't get as much attention as some of these. The key question is, can we somehow enable them to replace, augment, or even surpass DRAM? So we'll take a look at that. Let me give you some background first. Any questions so far? It's pretty interesting, isn't it? So you may see some of these technologies appearing soon. In fact, they're making their way to cell phones, not in terms of memory, but storage. So I'll draw this distinction between two types of memories. DRAM is definitely charge-based memory. Capacitor stores charge, and then you somehow sense that charge. Right? Flash is very similar, actually. It's different. Mechanisms are different in terms of how you inject charge and how you sense the charge, but it's still charge-based. Basically, you write some data by capturing some amount of charge, Q, and you read the data by detecting the voltage. Right? Resistive memory, these emerging technologies are all resistive. They do a different thing. They write data by pulsing current, dq over dt, and we'll see what happens with phase change memory. And you read the data by detecting the resistance of the cell, of the element that stores the data. So charge memory is limited because Well, it's difficult to place and control the charge. That's the exact problem that manufacturers are having with DRAM today. For DRAM, you have capacitor charge and transistor leakage. The charge basically escapes, right? And as you reduce the size of this thing, that charge becomes smaller and smaller. So it's very natural that it will become less and less reliable going forward, right? Flash is very similar. The charge gets trapped in the floating gates in Flash. So reliable sensing becomes difficult as charge storage unit size reduces, regardless of what kind of technology you have. This is true for SRAM also. SRAM is charge-based too, right? And very small, actually, people have run into scaling issues in SRAM before these technologies because they've actually integrated them on chip, right? But we're not talking about that. So let's take a look at some of these resistor memory technologies, and they operate a little bit differently in different ways. Phase change memory, which I know more about, and I know very little about this stuff, but you can read it. But let's talk about this one first. These operate by injecting current to change material phase. So you have a material that can exist in two phases. By injecting different currents at different amounts and at different lengths, you get into a different phase, as we will see. And resistance is determined by this phase. In spin transfer torque MRAM, this is magnetic memory, you inject current to change the polarity of a magnet, basically the orientation of the magnetic field. And the resistance is determined by the polarity, so you can sense that polarity, which is nice. Well, you can sense that resistance, sorry, not that polarity. And memristors, RRAM or VRAM, you can inject current to change the atomic structure. And resistance is really determined by the distance between the atoms, which is even more fancy, right? Well, I'm not sure which one's fancier than the other, but these are all complicated mechanisms. It's different from charge-based memory. So we're going to focus on PCM a little bit, and we're going to talk a little bit about STT-MRAM too. So what is phase change memory? This is actually interesting because this has been a technology that's been around for a long time. It's used in some rewritable CD-ROMs and DVD-ROMs. Well, we have this phase change material, chalcogenide glass, that exists in two states. Amorphous state has two characteristics. It has low optical reflexivity and high electrical resistivity, and the crystalline state has high optical reflexivity and low electrical resistivity. So people have used this first part to actually read data from CD-ROMs, right? Basically, you have an optical reader that can detect which state this material is in by sending light to it and looking at how much reflections you get. That's beautiful. And this operates. This has been used for, this is actually technology that was developed in the 1960s, early 1960s. We've been using that. But now, actually, people have developed mechanisms to detect the electrical resistivity in a reliable manner also. So any device, any memory cell consists of two components. One component is how you store the charge, and the second component is how you actually detect the charge. Well, I shouldn't say charge. How you store the value and how you detect the value. In DRAM, how you store the value is the capacitor. How you detect the value is the sense amplifier. This is also called an access device, actually. You can think of the sense amplifier as the access device. And the access transistor is that part of that access device, actually. So you can think of you can think of DRAM this way also. So people have developed these access devices, which we're not going to go into, that are actually relatively reliable and that's relatively fast. So now you can detect the resistance of this material very quickly today. You don't need to detect the optical reflexivity because that requires a lot of different components that you cannot integrate on chip today. But we'll detect the electrical resistivity. And this is what the material looks like. You have this chalcogenide glass, and you have these two metals, and that's the bit line. And this is the access metal, and you have a heater. Basically, you can inject current this way, and you heat up the material such that you can change its state. And we'll see how much you need to heat up this material. So you can think of this as high resistance state encoding a 0, and low resistance state encoding a 1. And because today technology has developed such that you can switch between the states reliably and quickly. So how do you actually switch between the states? Let's say you want to write. Basically, you change the phase of the material by injecting current at different ways. To set, you basically inject current in a sustained manner, this way, for a long time. And you heat the cell above this crystallization temperature. And after that, you basically set. To reset, basically, with one of this is 0, one of this is 1, you could think of it that way. You heat the cell with very high temperature, you inject a lot of current, and you melt it above this melting temperature, and then you quench. So it looks like this. Make sense? That's how you write to a 0 or 1. And you can encode it either way, right? It doesn't matter. That's why it's called set and reset. And for reading, you detect the phase via material resistance. And that's the access device, which we're not going to talk about. And this is actually real. People have produced this. This is pictures from IBM. This is the set state. This is the crystalline state. It's low resistance. And the resistance is 10 to the 3 to 10 to the 4 ohms. And this is the reset state. This is, as you can see, it's small current, and this is high resistance over here. And this is exemplified by this mushroom cloud, if you will. You'll see that in many phase change memory device papers. Okay, so this is actually built, and this operates. So let's take a look at the opportunity from an architecture level. There are people who are building the devices, and that's not the subject of this course. And you can take another course that talks about these. But let's take a look at some of the advantages of this, and we'll also cover some of the disadvantages too. Basically, the first thing is it scales better than DRAM and flash. It requires current pulses which scale linearly with feature size. And this is actually old data. It's expected to scale to less, even smaller than 9 nanometers today. It's prototyped at 20 nanometers by IBM, and that was in 2008. So DRAM reached 20 nanometers in 2013 or so. So you can see the difference. It can be denser than DRAM because you can actually store multiple bits per cell due to the large resistance range. If you look at this, the resistance range is from 10 to the 4, let's say, to 10 to the 6. That's a large range. The way you can store multiple bits per cell is by chopping that resistance range into multiple pieces instead of 2 pieces, right? If you actually have a single, so you could think of, let's see. Instead of storing 0, 0, and 0, 1, you could, so this is a 1-bit cell. Your resistance range is, let's say, from 10 to the 3 to 10 to the 7 ohms. You say anything that's below 10 to the 5 is a 0, above 10 to the 5 is a 1. Well, that's one way you could do it. You could be even denser if you could do something like this, if you could detect resistance at a finer grain, right? This is 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, 10 to the 7. If the resistance range is between 10 to the 3 and 10 to the 4, you say 0, 0. 10 to the 4 to 10 to the 5, 0, 1. 10 to the 5, 10 to the 6, 1, 0. And you could encode it in different ways, and 1, 1. Now you've stored 2 bits per cell, right? Depending on the resistance. Yes?
How can you get the material to be somewhat between its amorphous state and its crystalline state?
Yeah, so
it's like it's highly idealized that you could.
So you could actually do that. I made that picture idealized. It's actually in a different way, depending on how long you program. These actually, this is very similar to Flash. Flash is programmed this way also. Well, in Flash you store charge of course. But what you can do is they're programmed using iterative programming methods, and you program a little bit, check the resistance. Program a little bit, check the resistance. Program a little bit, check the resistance. That way you can actually get into these different states. Flash is that way also.
So you're
Yep.
severely sacrificing speed then in order to get higher capacity in that case?
So that's right. There is some speed sacrifice, but for reliability reasons, it's done this way anyway, actually. Because even here, you program it for a while and then check the resistance, because not all cells, because there's a lot of variability in the cells. Not all cells. This picture is kind of idealized for one cell, but for different cells, you need different times. That's the reason the programming circuitry takes these iterations to ensure that the data is actually to ensure that the cell is actually at the right state. Make sense? So you get this kind of for free. In fact, Flash is this way also. In Flash, you don't have this resistance range, but you actually have a voltage range because you detect voltage, right, in Flash. And what happens in Flash is the Flash controller. It's programmed using incremental step pulse programming. You basically pulse some charge, and the controller reads it and checks the charge, checks the voltage. And if it's not enough to bring it to some value, it injects some more charge. So it's incremental. Flash is very interesting too, but unfortunately we're not going to cover it in this course. So you can see that, and actually if you could chop it up even finer, you could store 3 bits per cell. Today we have Flash with 3 bits per cell. So you need to have, of course, 8 different partitions over here. And people have prototyped PCM with 2 bits per cell in 2008, and I think this is happening already. You can see that this is an old slide. And this is non-volatile, which is a big advantage, right? Because the state doesn't leak because it's not charge-based. It's really state-based, right? It's really phase-based. So it's shown to retain data for 10 years at 85 degrees, for greater than 10 years, actually, which is nice. And no refresh is needed because of this. You get low idle power. So we actually, I'll give you some data that we had done as part of research a long time ago. We started looking at it in 2008. And we wanted to look at the properties of this. Basically, we surveyed prototypes from a bunch of circuits and device conferences, which are kind of cryptic sometimes. And we tried to derive average parameters for PCM, phase change memory, at 90 nanometer feature size. 90 nanometer because these are prototypes. Right? And this is the table. And this is going to be on the exam. I'm just kidding. Basically, this shows that these are different parameters of the technology. Cell size is one, access device, read time, read current, read voltage, read power, read energy, set time, blah, blah. So you can see how complicated it is. Reset energy, write endurance. And these are different papers that have actually developed prototypes. And you can see it's very varied, actually. Some of these show, let's see, set time is 100 nanoseconds over here, set time is 80 nanoseconds over here. Here it's 400 nanoseconds. That's what happens with an emerging technology. Whenever you're looking at an emerging technology. As an architect, you should always be on the lookout for emerging technologies because those are interesting, right? You can build a much better system if you actually have a better technology to build your system with. And if you're too late to adopt the technology, maybe you lose, right? So everybody moves to phase change memory and you're still dealing with issues with DRAM. So this is interesting, but all this shows is it's not very clear what the exact parameters are, but we're going to assume some parameters. In fact, this is the most complete data, I think, as you can see. In some of the papers, you don't even have complete data. Because in some cases, when you have an emerging technology, either you don't know or you don't want to disclose. Okay, but let's look at the big picture. If you look at phase change memory, its latency is comparable to DRAM, actually, but a little bit slower, and I'll give you some exact numbers. So it fits over closer to here. And this is the spectrum of latency. This is latency to access, typical access latency in terms of processor cycles for a 4 gigahertz processor. DRAM is around here, between 100 to 500 or maybe more. Phase change memory is very close, 2x or so. Flash is far away, hard drive is even far away. And this is an exponential scale, as you can see. And this is SRAM, and this is EDRAM. So we're going to assume some of these parameters. Read latency is 4 times that of DRAM. But it's 1,000 times faster than NAND flash. Write latency is 12x of DRAM, and it's actually comparable to flash a little bit, but no, it's still faster than flash. Write bandwidth is 1/10 of DRAM and comparable to flash. We're going to assume these parameters, and these are derived based on the previous messy chart. One unfortunate thing is dynamic energy. So this is for reads and this is for writes. Reads consume 2x the energy of DRAM, and writes consume 43x the energy of DRAM. Well, you can guess why, right? Basically, you need to heat up to a very high temperature. Endurance is a problem. Why is it a problem? Endurance means basically how many times you can write to a cell. Well, it's a problem because writes induce phase change at 650 degrees Celsius. What happens is, as you heat the circuitry up to that, contacts degrade from thermal expansion and contraction. As a result, every time you do a write, you're taking away something from the cell. So we're going to assume 10 to the 8 writes per cell. DRAM today is practically infinite, which is not actually correct, but people have assumed DRAM as the memory with perfect endurance. The cell doesn't degrade, which is not true, but we have there are no documented effects for this, at least in the long run. NAND flash actually has endurance, which is about 10 to the 5 writes per cell, which is reducing. If we had a lecture on NAND flash memory, I would show you that actually you could write to a cell, very aggressive NAND flash cell, only 1,000 times.
So if you have to write to it and that makes it really hot, is that kind of a bad idea around the rest of the computing all this run slower?
So that's right. Yeah, that's one of the problems with phase change memory to replace DRAM. That's why some other technologies are more interesting today, in my opinion. When we first started, some of these issues could have potentially been solved, but they're still around, unfortunately. So that's a very good point, though. This is one of the reasons why phase change memory is not getting as much traction today, but it's still good to know. because this write is very power intensive. As a result, that limits your bandwidth, because you can do only so many writes at any given time, and maybe you need to have better cooling mechanisms if you want to get more bandwidth, right? Okay, cell size, I'm going to skip this, but the assumption is that cell size is going to be much better than DRAM going forward. This is always hard to argue because DRAM is a very mature technology, right? People have worked on it for 40 years or so, but this is not a very mature technology yet. Even right now, it's not a very mature technology. We don't manufacture phase change memory in big fabs today. So let's take a look at, as an architect, it's always good to abstract what are the pros and cons, right? Basically, pros over DRAM, you get better technology scaling, non-volatility, and low idle power. Cons, unfortunately, higher latencies, especially write latencies, higher active energy, and I'm going to increase this to 50x, especially write, and lower endurance as cell dies after 10 to the 8 writes. So can we somehow work with this technology and enable phase change memory as a DRAM replacement or helper? Somehow mitigate the shortcomings of phase change memory and find the right way to place phase change memory in the system and ensure secure and fault tolerant operation, because actually this leads to security issues as well. If you have low endurance, maybe you have some application that keeps writing to memory, and some other application, when it needs the memory, it doesn't find that memory exists anymore. Right? It's terrible. That's a problem with flash, actually. Once you keep writing to your flash devices, USB drives, I don't know when you will lose data, but you will at some point. So let's take a look at some of the, well, I'm going to go through this relatively quickly, but where to place phase change memory in the memory hierarchy is an important challenge. And some of these are actual design challenges today because people are looking at doing this. And whenever I say phase change memory, think about some other technology also. Maybe there's some other technology that's interesting, which I'll tell you one more. But there could be some other technology, maybe a different kind of DRAM, right? That could happen too. So do you expose it to the operating system? Maybe you have some amount of phase change memory, some amount of DRAM in the system and expose it to the operating system. Maybe you have hardware-controlled DRAM now and operating system-controlled phase change memory, or maybe you have pure phase change memory-based main memory. And we'll take a look at both options over here, these two options at the bottom. How do you mitigate the shortcomings? How do you minimize the amount of DRAM in the system if this technology is becoming very, very expensive? How do you take advantage of byte-addressable and fast non-volatile main memory? I think this is a very interesting direction going forward if you can do this. And can we design techniques that are agnostic to the specific non-volatile memory technology? Maybe phase change memory has different characteristics than some other technology, and we'll see that. So this is a cartoonish picture of what you have today, what you'll have in the middle, and what you have in the future, maybe, if this pans out. So this is probably more reasonable in terms of going into the future, because DRAM, it turns out, is very difficult to replace. So this is the hybrid phase change memory and DRAM solution. The key problem is how do you partition and migrate data between phase change memory and DRAM. But when we first started looking at this with my collaborators, we're a lot more aggressive, and we're going to examine this solution first. Yes.
The reason why instead of trying to replace DRAM, researchers have been looking to try and replace long-term storage like solid-state drives and phase change memory.
So yeah, people are looking at that also, and I think that's a great direction. But that's less of an aggressive direction, in the sense that it's clear to me that flash can be easily replaced with a technology like phase change memory, and there are fewer interesting research and design issues over there, and people have demonstrated that. But it's much more difficult to do this, right? And in research, you would really like to focus on the more difficult problems. And we will see how difficult it is, because when we first started, we looked at this, and right now it's difficult to do that. Unless you have a technology that looks like DRAM. Although actually, I'll show you some results with STT-RAM, which is not too bad with this case. Okay, so if you have a hybrid memory system like this, there are a lot of interesting research issues and design issues, which we will not go into actually. How do you partition the data? Should DRAM be a cache or main memory? Configurable? What fraction of the system should have DRAM? What fraction should be PCM? How many controllers do you have? How do you do the data allocation and movement? Who manages it? What are good control algorithms? How do you prevent degradation of service due to wear out? How do you maximize energy performance and lifetime at the same time? How do you design the cache hierarchy, memory controllers, and the operating system to mitigate the shortcomings of phase change memory and exploit its advantages? And how do you actually design even the PCM and DRAM chips and modules itself? So this is actually cross-cutting, and I will show you a later picture toward the end of this lecture. How do you rethink the design of the entire system, including the chips with the new requirements? So there are a lot of issues here which we will get back to, but let's take a look at some data over here. What happens if we actually take phase change memory and drop it into the system without changing anything at all? And that's not going to work, as we will see. But then the key question is, how do you actually redesign the entire hierarchy to overcome these shortcomings? And I'll assert that it's not going to be easy. Oh, wow. Should I talk about this here, or should we get back to it here? I'll talk about it here. I'll take you away from the data for a while, and I may show you this data later. But STT-DRAM works in a very different way. It's still a technology that's different from DRAM. Basically, what you have is you have this magnetic tunnel junction material, and you have some free layer, and you have a reference layer, and a logical 0 is stored if free layer and the reference layer align. Basically, it's the polarity of the magnet over here. If they're different, then you have a logical 1. And I'm not going to go into this, but the access transistor and bit lines are similar. To read, you apply small voltage across the bit line and sense line, and you read the current. To write, you need to push large current through this magnetic tunnel junction, and that changes the direction of the current. And the direction of the current determines the orientation of this free layer. You can change the direction of this free layer where the current is flowing. It's either flowing this way or this way. And you have the reference layer that's fixed depending on whether these are parallel, this is the parallel case, or anti-parallel. You can encode as 0 or 1. And you can sense that. And this is actually interesting technology because it has some better characteristics than phase change memory. It has better technology scaling, non-volatility, and low idle power. Cons, you have higher write latency and higher write energy. Reliability is still a question over here. But you don't have the wear-out problem. And we will see in the next few slides that wear-out problem is a big problem. OK. So let me show you some results, and we'll take a break before we go into the hybrid memory systems. What happens if you take phase change memory that has these characteristics, latency, read latency 4x higher than DRAM, write latency 12x higher than DRAM, endurance of 10 to the 8 writes, a cell dies after 10 to the 8 writes, read energy 2x of DRAM, write energy 43x of DRAM, and assume that you can take a DRAM cell out and replace it with a phase change memory cell in, keep everything else the same. Well, these are the results. If you do that, we've simulated this, and we organize phase change memory the same as DRAM, robobuffers, banks, and peripherals exactly the same as DRAM. Nothing changes. And these are some applications. These are actually scientific applications. This is an earthquake simulator, for example. This is shallow water image modeling. There are a bunch of other things also here. Conjugate gradients, for example, FFTs. And you see, for these applications, performance degrades by 60%, which is pretty bad, actually. You don't want to get rid of your DRAM for a 60% performance degradation. And energy increased by 120%, which is also pretty bad. And what is even worse is your memory dies after 500 hours. Why? You basically keep writing into memory, right? These applications have some write intensity. And assuming, let's say, you can do 1 write every 100 nanoseconds, well, 10 to the 8 writes are not that hard to do. Right? So this is terrible. And you have no guarantees. So you need to do something better than this. You cannot do this. Yes?
How do you tell when it dies? How do you know?
So the assumption is that after 10 to the 8 writes to a cell, it's dead.
Okay.
Yeah.
So if let's say you're your flash drive or whatever, how would you know if your flash drive died?
So what flash drives today have is they can track of these cells that die. So what they do is they do several things. They do wear leveling. First of all, what they do is they try to ensure that all of the physical cells receive the same number of writes. So they do a lot of remapping of data internally at the flash translation layer such that physically all of the cells have the same amount of writes, on average, of course. That's called wear leveling. That's the first thing. And if you have too many writes, what they start doing is basically they start taking out some of those blocks that are dead, so they can detect those. And at some point, they can probably provide something. Yes. So in this study, actually, there is wear leveling. This is with wear leveling. And lifetime is actually, this is not the entire memory. This is actually for 10% of the memory. But this is still 10%. You can multiply it by 10. 10% of memory degradation is pretty bad, actually. You don't want a 4 gigabyte memory to go into 3.6 gigabyte memory. Okay? So there is perfect wear leveling assumed here, which is another issue, actually. How do you actually implement perfect wear leveling at the memory level? Right? You need some flash devices today can do that because they have this flash translation layer, and they have a processor basically in the flash translation layer that does this wear leveling. And you can do that because the latencies are so high. if your latencies are on the order of 50 nanoseconds, then your wear leveling needs to be really fast, right? You could potentially do it in the operating system level in a coarser grain also, but that's a very good question. Okay, so how do you actually fix this problem? Let's try to fix it a little bit. I don't think we're going to fix it easily, but one idea. So the problem really happens, if you look at DRAM and phase change memory, the problem really happens when you access this array in phase change memory, right? Because this is what's slow. The sense amplifiers, the row buffers, are kind of similar in phase change memory and DRAM, actually. You still need to have row buffers to get the data out. And they don't operate exactly the same way, but we're not going to go into that. What you can do is you can reorganize these row buffers in a different way in phase change memory. Why? Well, DRAM, when you do a read of a row, it's destructive. You need to store the entire row, right? Because otherwise the row gets destroyed and you cannot get the same data. Whenever you read a row, you need to buffer the entire row. In phase change memory, it's non-volatile. You don't need to buffer the entire row. Actually, you don't need to buffer anything, but normally you buffer something such that you can get data out quickly from the chip. So your row buffer can be smaller, but now you can have many, many of these row buffers. So for the same amount of area in DRAM that's dedicated for the row buffers, for a single row buffer, you can actually have many smaller row buffers in phase change memory. Now if you do that, what happens is now you can manage this as a cache, as a small cache. Now you have multiple narrow row buffers. This can reduce the array reads and writes because you manage this better. You get better endurance, better latency, and better energy because this doesn't degrade. This is still as fast as DRAM because it's a row buffer, right? It's SRAM-like technology. It can be exactly the same actually, these latches. The second is you don't really want to write into the array. Not only you don't want to read from it, you don't want to write to it. So you would like to minimize the writes. Basically, you can keep track of the bits, if you will, that have changed. And you can write only those bits that have changed instead of writing everything. So in today's DRAM, well, basically in DRAM, as we've just discussed, you write the entire row buffer back to DRAM, right? If you do it right. Because that's how the technology operates. In PCM, however, you don't need to do that. You can even track of the bits. In fact, Samsung has, and other companies have chips that do this automatically on the chip. They basically compare the incoming data to what already exists, and they write back only those bits that have changed, because where is a big issue over here. So if you do these in some way, these are the results that you would get. Basically, your performance degradation goes to 20%. Take this with a grain of salt, but your energy is on par with DRAM because you reduce a lot of refresh. It depends on how much refresh energy you assume in DRAM. And these applications actually don't exercise memory as much. And you get a lot higher average lifetime. And the hope is that scaling will improve energy, endurance, and density. But there are a lot of caveats in this study. It's very difficult to do this kind of studies without knowing the exact parameters of the underlying technology. First is worst case lifetime is much shorter. If you look at this, there are some applications that basically kill your memory within a year, even less than a year over here, even with the mechanisms that are employed. Intensive applications see large performance and energy hits. If they keep accessing memory, they see large performance and energy hits. And perhaps we use optimistic phase change memory parameters. Right? It's very difficult to know this because it's not clear what the parameters are. So because of this, going forward, I think it's going to be very difficult to use a single technology like this as part of, as your only main memory component. So it may make sense to look at something like this because no technology has all greens. And technologies have different greens and different reds. And you can imagine some other technologies. STT-MRAM fits somewhere over here. So we'll talk about this in the next, I guess, in the remaining time. But perhaps we should take a break such that you can get cookies from here. Who didn't get their cookies? I guess, was it Jiang? No? You're not here, Jiang?
No, he's here.
Oh, who hasn't got the cookies? There was one person who didn't get their cookies. Oh, Xingwei? No? Okay. No? Well, I guess he loses the cookies. You can have his cookies too. So let's take a break for, let's see, I don't know what that is. 5 minutes? And in the meantime, feel free to get cookies from here. And then we'll finish the lecture. It's not going to take too long. see. Oh yeah, that's right, Jing.
I have a question. Wow. Oh, that's crazy.
God,
So
what is going
I've
on?
been like sitting there
Uh-huh.
trying to like write programs that do the memory controller overload thing that you were talking about. And I just like have one that, you know, I allocated a bunch of memory, right? And then I'm just streaming through it, writing a bunch of like random numbers to it so that it's always different and stuff. But everything still seems to like function okay.
Yeah, what you need to do is, I can send you the paper actually that we were sent. So you need to, what happens is because you don't always access memory, right? You need to bypass the caches somehow.
So what if I stuck in a bunch of mallocs and freeze so
Yeah.
I'm getting different locations?
Yeah, still it doesn't work. You need to really know. So what you really need to know is you need to keep exercising the same row in the DRAM.
Okay.
And you need to also ensure that you don't get data from the robot. Because if you get data from the robot first,
Then it's
it
gonna
doesn't
be-
work. Yeah, you need to activate basically.
Okay. So that's kind of harder.
That's right.
Okay.
It's harder. It's not as easy. It turns out it exists in real programs actually, but in some cases, not in many cases.
Alright.
But if you figure it out, I'd be curious to. And maybe your DRAM is old. That's another possibility, right? If it doesn't work. I think it's probably because you haven't written the correct program.
Wait, if it's old, why would that make it?
So this is happening in recent DRAMs.
Oh, why did it not occur before?
Because scaling is not as big of a problem for the manufacturers. They were able to keep these errors under control. But now
Oh,
they
no,
cannot
no,
test
no.
it.
I'm talking about the one where the memory controller keeps only like one thread starts out.
Oh, I see. So even
By
that's hard.
submitting
Yeah.
so many requests.
Yeah, it's the same thing. Again, it's the same thing. You need to have the right intensity.
Yeah. Okay.
You need to conflict in the bank.
Yeah. Okay.
So you need to do a controlled study. Now you may need to do some reverse engineering to figure out how the
Yeah.
memory is mapped.
Yeah, exactly. Okay. Cool. Thanks.
Just take the cookies off, double the grid. Like on. One time in a 650. Oh, you just stacked it. Yeah. Oh, man, that's so I didn't actually do that. I'm not trying to do that.
You can try it.
If you like, just like sub.
Out of curiosity.
I was thinking about. Oh my gosh. Oh. You're just giving up? Come on. Dude, what are you doing? Cranberry citrus oak. I have to know. Are you I really want to try one of those Turkish goods. Ready? Oh yeah, you came in late. Those Turkish cookies.
I ran out of this quote because my backups were backing up my backups.
You know what? This thing called Git must be pretty awesome.
I use Git.
Why are you using Git?
Wait, what happened?
Well, I mean, I use it on my home computer. So, but then I just like, but I clone it to like the best ways to.
Yeah, I get that. Why do you have more backups?
So, the
guys did not even open this.
old files directory, that's there are old files in my old files.
So the only super big mistake I made there was not deleting output for like before, which is really stupid, and creating 100 megabytes of 140 megabytes of tests for 340 and then trying to push them.
Yeah, that's
a ton of systems to fix that.
All right, let's get started. So we're going to talk about some things in these hybrid memory systems. There's a huge design space here, obviously, which we're not going to cover. But going forward, you can bet that your memory systems will look like this. Basically, the key problem over here is, well, certainly there are many, many key problems as I've discussed, but assuming that you fixed your technologies and you fixed how many controllers, how much amount of memory you have, then the key problem is how do you actually design the hardware and software to manage this data allocation and movement to achieve the best of multiple technologies, right? But you can imagine many, many other design questions. First question is, who manages these things? And I'm going to cover DRAM as a cache for phase change memory, and it will be a hardware managed cache. Another option is you divide the address space, software visible, OS visible address space between DRAM and phase change memory, right? And OS somehow manages it. And you can do page migration, for example, between DRAM and phase change memory. But that may have a lot of software overheads because these are really fast technologies, right? If you want to migrate between this DRAM to that DRAM, the overhead of migration in terms of the software could be even higher than the time it takes to migrate the data, right? Because you need to go into the software that needs to initiate a routine that does a page copy. Right? Okay, so we're going to assume this. We're going to assume that phase change memory is main memory. That's your entire main memory. And DRAM cache is memory rows or blocks. The benefit of this is you get reduced latency on DRAM cache hit. And DRAM cache can act as a write filter. Basically, in DRAM cache, you can have a policy that tries to minimize the writes that go into phase change memory. And if you have a 1 gigabyte DRAM cache and 32 gigabyte phase change memory, it may be okay. Maybe you do good wear leveling also at the same time, such that you don't destroy your main memory in this case, which is phase change memory. And memory controller hardware manages the DRAM cache. The benefit of this is it eliminates a lot of the system software overhead of managing DRAM. Right? Today, DRAM is managed both at the hardware and the software. Whenever you need to bring data into DRAM, you need to go through software from the disk, right, or from the SSD. We don't want to do that. We don't want to bring data from phase change memory to DRAM through the software. We want to do it through the hardware. Basic hardware determines what data should be brought. It's just like a cache, basically. You can think of it as your L4 cache. DRAM is your L4 cache, right, or L5 cache. There are three big issues over here, which I'm not going to talk about all. But the one issue is what data should be placed in DRAM versus kept in PCM, phase change memory. And we're going to cover this a little bit. What is the granularity of data movement? Do you move data in terms of pages, like 4 kilobyte or 8 kilobyte? Well, this is going through the memory channel, right? You can saturate that memory channel quite quickly if you actually move data, move big quantities of data. Maybe you should really be doing it at 64 bytes, at cache block granularity. But again, there's no one-size-fits-all here. Some applications like moving big chunks of data, some applications like moving small chunks of data, because some applications just use very small chunks, and some applications use big chunks, right, if you're streaming through memory. Well, we'll see some other solutions for streaming through memory. Then the third thing is, how do you design a huge DRAM cache at low cost? You probably want your DRAMs to be large, right, still. You can have a more scalable phase change memory that's on the order of 32 to 64 gigabytes, let's say, but your DRAM will not be 32 megabytes. It will probably be much larger than that. And once you have a much larger cache with a block size granularity with small blocks, then your tag store becomes a problem, right? Imagine you have a 4 gigabyte DRAM and you have 64 byte blocks. Your tag store becomes really big, right? How many sets do you have? Or how many blocks do you store in that? 4 gigabytes is 2 to the 32. 64 bytes is 2 to the 6. You have 2 to the 26 blocks in that cache. So your metadata overhead, tag overhead becomes large. And these are all real issues in designing a system like this. In fact, IBM has EDRAM caches, for example, that are managed in hardware that are pretty large, that are not as large as 4 gigabytes. But they still need to solve this problem. How do you design this large DRAM cache at low cost? One thing that makes life easier for them is they have these large line sizes, cache block sizes, that reduces the tag overhead significantly. Okay, so there are two solutions, which I'm going to talk about only one of them over here. What data should be placed in DRAM versus kept in PCM. And I'm going to give you one insight that's actually applicable to many different memory technologies. And it should be obvious by now to you because you know the structure of any memory technology really well. If you look at this, you can abstract any technology as a bank that actually consists of cells that are made in that technology and a row buffer that consists of cells that are made in a different technology, SRAM-like technology, right? And this row buffer is essentially the same between phase change memory and DRAM. What is different is really the bank itself, because the bank here is fast and energy efficient, and it doesn't wear out. Bank here is slow, energy inefficient, and it wears out. So once you make this observation, you also see that row buffer hits latency is the same in DRAM and phase change memory, right? So if you keep hitting in the row buffers for some data, maybe you shouldn't place them into DRAM cache because you'll get the same latency over here. Right. So that's the idea over here. Accessing the row buffer in phase change memory is fast. What incurs high latency is the array access of phase change memory. So you would like to avoid this. If you keep accessing something in the array, maybe you should put them into DRAM such that you can access them from the DRAM array over here, because DRAM array is much faster. Whereas if you keep accessing something from the row buffer in phase change memory, it doesn't matter if you actually put it into DRAM cache. It's better to keep it in phase change memory because you get the same latency and you don't waste this valuable resource, right? Remember, this is valuable. You don't want to put data here which is not really critical and which you can access at the same latency over here. So that's the idea over here, row locality over data placement. The idea is cache in DRAM only those rows that frequently cause row buffer conflicts, because row conflict latency is smaller in DRAM, and that are reused many times, because DRAM is a cache, right? You don't want to put stuff into DRAM that you're not going to reuse. That's with any cache. Ideally, you would like to put only stuff that you're going to reuse in a cache. And this is applicable to many technologies. That's why I'm giving you this idea, basically. If you actually have part of your memory the same latency as part of this other memory in the system, whereas some other part is much slower, you would like to, and this memory is much more expensive over here, you want to keep in this memory the data that you're going to be able to access at a similar latency and bandwidth as if you put that data over here in the expensive memory, because you don't want to put stuff, you don't want to waste this expensive memory at all. So there's a rule of thumb, I think, that is even more important, which is if you're streaming through memory, which means that you may be getting a lot of row buffer hits, better to place that data in phase change memory. If you're not streaming through memory, but have some reuse, better to place that data in DRAM, at least in this case. And if you do this, you actually get reasonable results. So this is some data based on the simulation of these algorithms. And these are some applications. Actually, these are heavy memory bandwidth intensive applications. And this is an algorithm that the frequency mechanism, ignore the dynamic one. Dynamic one actually adapts some thresholds. Maybe don't ignore it, but it adapts some thresholds as to why you do this. You can imagine how you do this, right? First, you need to determine the rows that actually cause a lot of row buffer conflicts, right? You need to keep a record of them somewhere. And you could do that at the memory controller, right? And you could adjust the threshold of when you would actually decide to move that row to DRAM. If you keep getting row buffer hits, what is the threshold of how many row buffer hits you get to move that row to DRAM, right? And dynamic basically adjusts that threshold dynamically. Freq here is actually a mechanism that keeps in DRAM frequently accessed pages. So it's an old mechanism, but we're not going to talk about that. Actually, if you look at just LRU management, it's horrible. LRU doesn't do well over here because it's least recently used. It doesn't take into account because the data movement across the channel is a bottleneck. If you move a lot of data between the two caches, that's basically creating this channel bottleneck, which and channel is a bottleneck because other applications may need to access it, right? So LRU is not good because it keeps, whenever you access a block in PCM, you put it into DRAM. That may not be a good idea if the block is not going to be reused, if the block is not frequently accessed. So frequency-based mechanisms are much better in that case. And that's what their performance is over here. So if you do what I described, that improves performance by 17%. Put the streaming data into the row buffers, put the other data with some reuse, not row buffers, put the streaming data or row buffer hitting data into phase change memory, put the other stuff with reuse to DRAM. And 10% over here, 14% over here. And energy efficiency and fairness also improve. So where does this take us? Let me give you the bigger picture, if you will. So this is performance. Assume that this is performance. This is for 16 gigabyte phase change memory with these workloads. And this is the performance of 16 gigabyte DRAM. So there's a huge gap over here. And this is the performance of what I've described. That's if you allocate data as I described between DRAM. If you use DRAM as a cache for phase change memory. So we're still within in between, right? We haven't really bridged the gap to DRAM. DRAM has much higher performance. Yes.
How much DRAM do you have?
Oh, actually, I don't know. Do you know, Archada? I don't remember. But I believe it's meant to be equivalent. Not equivalent, but DRAM is much smaller.
Yeah, okay.
So maybe 1 is 15, something like that. But Archada might remember. He doesn't remember. Okay. So people have shown, let me give you the data point that I remember. People have shown that if you have 1 gigabyte DRAM and 8 gigabyte PCM, you see similar results to this. So the hope is that, well, that's basically you're in between. The hope is that in this system, or here, phase change memory can be much larger, right? Because it's much more scalable. That's the hope going forward. So you can have 64 gigabyte phase change memory here, and you get overall better performance. But we're still not there yet in terms of if you compare the technologies with same sizes. Okay, any questions? Let me move to some other opportunities with emerging technologies, especially not, yeah, no.
Actually, if we see ourselves going towards using DRAM as some sort of cache between PCM and, I guess, the processor, do you see that DRAM is going to start to shift from capacity to more speed? So maybe, because right now it's been focusing on, as you said, like capacity, Excel or whatever. But if you make it really fast and still fall under this like 1 gigabyte threshold, then it can be better.
That's certainly possible, actually, going forward. So my feeling going forward, DRAM will be more specialized. And what you're saying is one form of specialization. If you use it as a cache, maybe you should make it as fast as possible. Well, maybe at a reasonable cost. But I also feel that this is not the only solution. Maybe there are other technologies. Maybe you have heterogeneous DRAMs in the system. Fast DRAM and slow DRAM. That's actually, this should be appealing to DRAM manufacturers because that's how they can scale into the future. Reliable DRAM and non-reliable DRAM, for example. Energy efficient DRAM and not energy efficient DRAM. That way, now you can optimize the system. And actually, that could be a reasonable way to scale because you don't need a new technology for that. You probably know how to manufacture a lot of these things. But that's a great point. Okay, let me tell you some other opportunities because I think this is really exciting going forward. One is merging of memory and storage. Can we actually design a single interface to manage all data? And this is kind of going back to the old IBM systems, but we'll talk about that. You can have new applications potentially because if you have this fast non-volatile memory technology, perhaps you can checkpoint your state very, very quickly. Right? And this is a big problem if you're actually doing computations that are important and you're regularly checkpointing your system. In today's systems, if you have a large data center, let's say, with lots of memory, if you're regularly checkpointing your system such that you tolerate faults, you go back to the previous checkpoint if you see a fault in the computation, if you see a fault anywhere. That checkpointing takes a lot of time. Most of your time and energy is spent on checkpointing, actually, and recovery. But if you can checkpoint and restore your state very, very quickly, because this memory is really fast, right? It's right by your DRAM, right? It's not as slow as SSDs, and it's definitely not as slow as disks. Traditionally, this checkpoint has been done onto disks. Now SSDs have made it much faster, and this non-volatile memory can enable this kind of applications. Or maybe your boot up can be much faster, right? People have actually evaluated this. If you have phase change memory, well, you can boot up from phase change memory really quickly instead of going into the flash store. You can have more robust system designs. Perhaps you can reduce data loss, right? DRAM Actually, when you power off DRAM, it loses data. And if you have, for some reason, if you lose power, well, you can lose data. Whereas now you have non-volatile memory that's really close to processor, and you can keep things over there, right? You may have zero data loss. That's why people who design very fault-tolerant systems use battery-backed DRAM, for example. They back the DRAM with batteries such that it doesn't lose data. But it has its own reliability issues and it's costly. But non-volatile memory doesn't have that. And perhaps you can do processing tightly coupled with memory. Maybe you can have efficient search and filtering close to memory with some of these functions that I've described to you. Like if you can compare, for example, what we are writing is different. If what you're writing is different from what is in the row, maybe you can do some of these functions also. Well, let's take a look at this one because I think this is really interesting going into the future. This kind of shows you how you can rethink the architecture of a system with an emerging technology. If you look at a traditional system that looks like this, right? And we've covered actually this part of the system very, very heavily in this course. Basically, you have a two-level storage model. What is that storage model? You access working storage, main memory, that contains volatile data with a load store interface. And this interface today has virtual memory and it's heavily accelerated, right? Well, you have TLBs over here, for example. Page tables are cached. It's heavily accelerated by hardware. Persistent data, on the other hand, the data that you need to access after the system gets powered down, is stored in the storage. It's accessed via a very different interface. We have the file system interface. And there's a lot of overhead over here. Whenever you do an fopen, it takes a long time to actually get the data from here. And this model has developed because the medium to store the data over here and the medium to store the data over here have been extremely disparate in terms of latencies. Right? The main memory was really, really fast. Storage, traditionally, hard disk drives have been extremely slow. SSDs have reduced this a little bit, but still they're really slow. Now things change a lot if you do this. Take SSDs out of the system and put something like persistent memory. Now, once you do that, well, persistent memory, emerging non-volatile memory technologies like phase change memory. The problem is if you do this and keep the same model, this code that's executed every time you do fopen, fread, fwrite becomes bottlenecks because you need to have the code to locate, translate, and buffer data that does this, and they become performance and energy bottlenecks when this is fast. Now, most of your time is really not spent before. Most of your time is really spent accessing the device. And this is, yeah, it takes some time, but it doesn't take as long as the device access. But if you do this, now most of your time is spent here, and the device is accessed in 200 nanoseconds. So you're doing milliseconds of processing for, well, maybe milliseconds or microseconds of processing for 200 nanosecond access. That sounds like a bad idea, right? And that's exactly a bad idea, in my opinion. Basically, once you have something like this, maybe you should rethink the entire system design going forward. And it may make sense to do something like this. And this is just one example. Maybe we can unify the memory and storage management in a single unit, such that you eliminate wasted work to locate, translate, transfer, and translate data. So of course, when you do an fopen today, what happens is you get memory mapped file access, right? What happens is the system, the code over here, takes a long time to map portions of your file to memory, such that eventually you can do memory mapped accesses. Actually, if you care about performance, that's what you would do. But that requires a lot of data movements between the memory and storage, right, in SSD. So it is not like you're always accessing disk whenever you do an fwrite, right? It's all memory mapped. But even that takes a lot of time. So we're going to eliminate that. If you do something like this, you have basically a load store interface to all of your memory and storage. Now you don't need to do all of that translation. Basically, the hope is that this improves both energy and performance because you don't waste energy doing that translation and doing that location and doing that buffering. And hopefully, in the long run, you can simplify the programming as well, programming model, because you don't need to deal with files and memory separately. Today, these are very separate, right? You don't have data structures that are persistent today. Do you guys? Have you guys programmed with a programming language that has its data structures persistent? No, everything is volatile, right? Yeah. So going forward, maybe it's a good idea to change these. It's actually an old idea. It's really not that new. IBM AS400, for example. If you look at Frank Soltis, an IBM engineer, wrote a book it's called Inside the AS400. It's a beautiful book. It discusses all of the design choices they made to design the system. And he talks about exactly the same thing. Basically, you don't want your memory and storage to be different because you have all these overheads. So they've tried to do this, but now the problem is even worse, right? You have these memories that are very close to DRAM. So how do you actually design the system? So this is just some ideas. So I'm going to go through this relatively fast. If you have something like this, maybe you expose a load store interface to access all data, persistent data into world. Maybe you enable applications to directly access persistent memory. As a result, you don't have any conversion, translation, location overheads. Somebody manages this data placement, location, persistence, and security, and that could be the persistent memory manager. And I'll talk about this a little bit, such that you can get the best of multiple forms of storage. You need to, of course, manage metadata, storage, and retrieval. Where is this data located? Tag stores, for example, is one example. And this can lead to overheads that need to be managed, obviously. And you can expose hooks and interfaces for system software. So having a single interface doesn't mean that you cannot tag the data, right? You still want to know, perhaps, the programmer to tell you, oh, this data needs to be persistent. I don't want it to go away, right? Maybe the programmer can use these interfaces in a different way. So this enables better data placement and management decisions. So this is one example over here, and this is the persistent memory manager. The future may look kind of like this. You have these heterogeneous technologies, and maybe multiple different types of DRAM and multiple different types of NVM and flash, and you access things with a load store interface with some metadata related to the loads and stores, and maybe the portions of the memory pages. And it may not need to be a page-based management, right? Because now maybe you want to delineate logical objects in your memory. Today we manage everything on a page-based manner or file-based manner. Maybe you want to do it in an object-based manner. So if your programming language supports constructs like this, maybe you define some persistent objects. Oh, this is an important array, if you will. So I'm going to make it persistent. And you program such that when the program crashes, this data is still available because you said that this is persistent. Right? You don't need to deal with all of the files. The system doesn't need to deal with flushing the data from DRAM to the persistent parts of memory. This way, everything happens because you said this is persistent, and the persistent memory manager says, oh, I'm going to keep it in persistent memory. I'm not going to expose where I keep it because I'm going to manage the performance and latency and energy underneath here. But I'm going to ensure that this is persistent because programmer asked me to do so. Okay, so there are a lot of interesting issues as to how to design it, and people are looking at different portions of it today. So let me give you benefits of this. This is also called single level storage. Basically, you have a single level storage model. So this is one example, and take all of these with a grain of salt because these are all simulation results, but the order of magnitude matters here. This is what happens if you have hard disks and a two-level storage model. This is what happens if you replace the hard disk with non-volatile memory. So you get a lot of benefit. This is phase change memory parameters. And SSDs are somewhere over here. It's not evaluated here, but you can imagine it bridges the gap between hard disks and non-volatile memory. And if you actually get rid of this two-level storage model and have a single-level store, get rid of all of these processing overheads. So once you have, and we have two-level, most of the time is spent on the system calls for CPU and system call for I/O. That's basically overheads in the operating system and file system. It's not in accessing the device. And you get, basically, if you eliminate that overhead, you get 5x more performance benefit. And energy benefits are actually similar. So that's why this is an interesting proposition going forward. So it may be going back to the old days that people have written papers, people have written books about how we should actually have a single level storage model. The first computers were all single level storage models, right? Because memory was not a big bottleneck at that time. But now if you have storage that's really, really close to memory, this is also called storage class memory, by the way. That's also IBM's term. It's called storage class memory. It's storage class because it's non-volatile. Okay. I guess we still have time. So if you have a technology like this, you actually have many issues, and you can develop many ideas from all the way to technology layer to the algorithm layer. Remember, this is a picture that I showed you in the first class, I think. We're going to finish with that picture also. There are many things that you can do at all levels to enable non-volatile memory and hybrid memory and exploit this. Basically, how do you tolerate errors? You could do that at these levels, or you could do that at these levels, right? How do you enable secure operation? Wear leveling, for example. How do you detect a program that launches a wear out attack to your memory? Which level do you do that? How do you tolerate performance and power shortcomings? How do you minimize the cost of the system? You could have solutions at all of these layers. How do you exploit non-volatility is interesting. And what I've described is one exploitation of non-volatility. How do you minimize energy consumption? And how do you exploit MVM potentially on chip? Because there could be some non-volatile technologies that can be adapted on chip. For example, a spin transfer torque MRAM is a good candidate for an L3 cache even, when people are examining that. I'll focus on one of these challenges because I think there are interesting security or privacy challenges with this also. So limited endurance can lead to wear-out attacks. One program can wear out the memory. Non-volatility actually may be a bad idea in some cases, right? Data persists in memory after power down. Perhaps someone can easily retrieve privileged or private information this way, right? One good thing about memory is once you power it off, everything is gone. Well, actually it's not exactly true also, because as we've shown, as you know in this lecture, DRAM still keeps data, right? Because there's some retention time, and that retention time is different. And people have actually launched attacks. It's called memory remanence attacks. Basically, if you take someone's DRAM and cool it off right after it's powered off, you can reconstruct what's in DRAM partially, because a lot of the DRAM cells can still keep their data for a long time. And if you cool it off, they keep their data even longer time, because there's an exponential dependence between retention time and temperature. As you increase the temperature by 10 degrees, the retention time reduces by approximately 46% or 50% or so. So you can cool it off really a lot. You can do nitrogen cooling, I guess, and discover someone else's data in memory. Well, we're not going to talk about, but you can actually leak information if you have multiple bits per cell. There could be side channels. But basically, these are actually interesting problems, and perhaps there are ways to tackle that. You can better architect the memory chips to absorb writes. You can do better hybrid memory system management, and maybe you can detect these attacks online. How do you fix this problem? Well, maybe you can efficiently encrypt and decrypt the whole main memory, but how do you do that efficiently is a key question, right? And maybe you do better hybrid memory system management as well. And for this, you need to somehow hide the side channels, but we don't really have time to talk about it. Okay, any questions before I summarize? Otherwise, I'll summarize, and well, I guess this is the summary, basically. We've looked at some key trends affecting main memory. This is not all of them, but end of DRAM scaling is a big one that motivates these emerging memory technologies. Need for high capacity and need for energy and efficiency. These all motivate emerging motivate the use of emerging non-volatile memory technologies. And these technologies can help with some of these trends. Phase change memory is one example, but there are other examples as I discussed. Spin transfer torque MRAM and memristors are potential examples. They're more scalable than DRAM and they're non-volatile, but they have critical shortcomings as well that need to be managed somehow. So going forward, people are looking into, and maybe you guys will be looking into, enabling some of these technologies by overcoming their shortcomings. And there are a lot of opportunities to do that, I think, across the entire system stack. Because you can actually reinvent the entire main memory today. Like in the first lecture, I mentioned that you can reinvent the entire computing system today. That's true. That's true especially in main memory, because memory is such a big bottleneck that's really not scaling. That's running into all of these scaling issues even before some other parts of the system. And also, it's more important than some of the other parts of the system. For example, processing, we know very well how to handle. We know very well how to scale the processors, even though we don't know it perfectly. That's why we went to the multi-core, right? But at least it's less of a bottleneck in today's data-intensive workloads. Today's data-intensive workloads are really mainly bottlenecked by main memory. So there are many exciting opportunities to reinvent main memory going forward. I guess I'll stop here. Any questions? Is it interesting? Yeah. That's pretty interesting. All right. Well, if you want to learn more about it, we don't have any other lectures. You can take 742 if you wish. But that's all I have, and that's the end of lectures for this class. We'll have a final exam, like it or not. I hate to bear these bad news, but I can console you with cookies if you would like. There are still cookies over here. But yeah, thanks for being a part of this class for, I guess, 33 lectures now. And thanks for sticking until the end of it. Hopefully you'll all do well on the final exam. Okay, and make sure you fill out the course evaluations too. Okay. Well, hopefully I'll see you some other time. Feel free to stop by anytime, before or after the final exam, anytime.
What do you do with these cookies?
Well, someone eats them. Oh.
Unless you're gonna put them out.
I put them out normally.
Okay.
You can take several and put it in your pocket. You can even construct one little box for you. Yeah, don't leave the cookies alone. If you want, take them.
All right, thank you.
Yeah. They will be videotaped.
Oh, awesome. Good.
No,
I
that's
can't
why.
because conflicts.
Oh, so you just want to see the lectures?
Yeah, I might just watch the lectures then.
Okay, sure.
Also, I wanted to ask
Yeah.
about where I stand on the curve.